Section 16.6 or 16.7, depending what you're looking at. If it is Cal Poly, this is 16.6. If this is Pasadena, it's 16.7. It talks about surface integrals. So, if we're talking about Cal Poly, surface integrals, which is 16.6, to surface area, which is 16.5, is much like line integrals 16.1 to arc length 16.3. Note that surface integrals and surface area are the same if you take the function and you let that be 1. Surface integrals allow us to compute the mass of surfaces, the flow of a liquid across a membrane, or the total electrical charge on a curved surface in space. So, if g of x, y, z gives the mass density, mass per unit area, at each point on the surface S, the total mass is calculated by the double integral over S. Remember, those two are the same. If g of x, y, z, the function equal 1, this is literally what we did in the previous section. Now, if I was given S to be described by a vector, then I would use g and I evaluate those accordingly. And ds would be right there. That's the same as the previous section. If I'm given a vector r sub u crossed with r sub v, du dv. If I'm given z as a function of x and y, of course you could modify that to be y as a function of x and z. Then you would really replace z by the function, and you would take ds, which would be, or the rho, which would be the square root of f sub x squared plus f sub y squared plus 1 dx dy. So, I have an example on every scenario you can come across. Let's get those out of the way. Example 1. Integrate the given function over the given surface, i.e., meaning evaluate the surface integral. Now, they gave us a function z. So, what I need to figure out how is my surface defined. My surface defined as, again, I don't need the graph for that, but if I could visualize it, that would be really good. So I'm eyeballing, let me see, z squared plus, there's the z, there's the x. It's a circle with a radius of 3, and it runs between -1, so I should push that back a bit, and 4. So it is the upper half of a cylinder. There you go. That's what it looks like. This is 4, this is -1, this is 3, this is -3. So if I really glance at this, z is positive, I could say z equal the square root of 9 minus x squared. And I could say my description here is that r of x, y, the square root of 9 minus x squared, right? So r of x, y, z, I'm rushing, r of x, y, and z is really, let this be x, let this be y, let this be 9 minus x squared. Remember, I need to reduce that by 1. I know that y varies between -1 and 4. That's pretty good. And I know that x varies between -3 and 3. That'll do the trick. So what do I need now? Well, for every problem, I'm going to have to figure out couple of ways of doing this. I could take a derivative, but that's kind of messy, and I could show how to do that if you really want. Or I could take r sub x. R sub x is 1, 0, negative x over square root of 9 minus x squared. R sub y, that is 0, 1, 0. And if I take r sub x crossed with r sub y, that would be the I component plus x over square root of 9 minus x squared. The j component will be 0, and the k component will be 1 minus 0, right? So if I take the magnitude of that, again, they're right there. The magnitude of that would be the square root of x squared over 9 minus x squared plus 1 squared. So that is the square root of x squared plus 9 minus x squared over 9 minus x squared. That is the square root of, that is 3 over the square root of 9 minus x squared. So now I come in and I say the double integral over s of my g function. My g function is z minus x ds. That's going to equal, and let's see how that works. Z is the square root of 9 minus x squared minus x, and ds is the magnitude of that. And I could do this, it's right there. I could do this in terms of the x first. X runs from negative 3 to positive 3, and y runs from negative 1 to 4. And that'll do the trick. You could distribute that, and the radical cancel out. The second piece will be a u sub, and that's would be it. Now I do want to point out, I could have also said the double integral of z minus x ds, and I could have went on the side and said ds. Wait a minute, I'm given z equal the square root of 9 minus x squared. So instead of me finding a vector, I could just use that right there. I could say ds is, well, let's see, what is the square root of z sub x, that is negative x over the square root of x squared, 9 minus x squared, plus f sub y is 0, plus a 1 squared, right, dA. And I could have simply said this is the double integral. Z is the square root of 9 minus x squared minus x. And what do we have? If I combine f sub x squared, I didn't square that. And if I square that, isn't that identical to this? Isn't that really the same as 3 over the square root of 9 minus x squared? And I could run this again, dy dx, x run from negative 3 to 3, and y run from, and look at that, it's the same thing. Instead of doing all of that work. So if I'm given the function as a z, I should use the bottom, f sub x, f sub y. If I'm given the vector as, if I'm given description as a vector, I should use r sub, I shouldn't cross over. That's a lot of work, but I could if I want. And I just showed you that on the first example. I'm not going to do that on every problem. So when I get to the second problem, if I really wanted to proceed, again, I could say if I want, oh look, let me tell you what this graph looked like. Again, I could do this both ways. This is a cone cut off at 4. There it is. So I could look at this and say, well, I could define this easily by, look, R of U and V is, now just be careful, you gotta be able to describe the surface. I could say this is U the cosine of V, U the sine of V, and just, let me think, Z runs between 0 and 4. So 0 to 2 pi and U. And I could say that U run between 0 and 4, and V run between the whole thing, 0 to 2 pi. That's one way of doing that. Then what that means, I have to find R sub U. R sub U is negative U, nope. R sub U is simply the cosine of V. And the sine of V, and a 0. R sub V is negative U the sine of V, U the cosine of V, and a 1. And if I take the cross product, the I component is going to be sine of V minus 0. The J component is going to be negative cosine of V minus 0. And the K component is going to be U cosine squared of V plus U sine squared of V. So this is going to equal sine of V negative cosine of V. And if I factor a U out of those, that's cosine squared plus sine squared, which is 1. So if I take the magnitude of R sub U crossed with R sub V, that is the square root of sine squared of V plus, when you square that, that becomes a positive cosine squared of V plus U squared, which is 1. So the double integral over S of twice the square root of x squared plus y squared, that's going to be, let me just get that way. And there. And that's going to equal twice the square root. And if I put that in there and that in there, what do I get? I'll get, I just noticed that I messed up. No wonder it's not matching. That's a 1, by the way. That's a 0. R sub U, that's a 1. R sub V, that would be a 0. So really quick, if I get this again, not going to change much, but it will change. So the I component is U the cosine of V negative. The J component is 0 minus positive U the sine of V, and this will be U the cosine squared of V plus U the sine squared of V. So yeah, this would be, there would be a U squared there and a U squared there. So that will be U squared times 1 plus U squared, the square root of 2U squared. There we go, much better. I knew something wasn't adding up. I was looking at that and thinking, wait, what's happening? Why is it not working? So this is twice x squared plus y squared. We know that is that's just U, right? If you put that and square it, that and square it, factor the U squared, that is just U, plus x squared, that is U the cosine of V squared, of what? Of radical 2 times U, that's this, times du dv, and it doesn't matter in which order you do this unless you can integrate. V runs from 0 to 2 pi, and U runs from 0 to 4. Now, if I wanted to use the square root of f sub x squared plus f sub y squared plus 1 squared on that? I could. I just need to be able to find limitations on x and y, and if it's a circle, it's not wise to use rectangular because then you're going to have a square root and you're going to have to use that trig substitution, which most students don't prefer, but it's doable, of course. Theoretically, you could do each of those any way you like. If I wanted to look at this piece right here, I was debating if I should stop and make the next 3 problems a new video, but I think that's going to be about 10 minutes. So we'll do them here. So let's look at how this appears. Z equal 9 minus x squared. Z x 9. 3 negative 3. Z is positive and you run to 2. There it is. A piece like that. Okay, well, how does that work? In this case, I could see how I could describe easily with f sub xy. So I could say ds, which is the row, that is the square root, f sub x, f sub y plus 1. So d sub s is the square root of 4x squared plus 1. So the double integral over s of g of x, y, z, ds, or d rho, that's going to equal the double integral of x is x, and y I don't need to worry about. That's perfect, actually. They stay the same. There's no z in the equation. Times ds, the square root of 4x squared plus 1. Of course, there's a dA there. And here I could say let y run from 0 to 2, and let x run from negative 3 to 3, and that'll do the trick. That's pretty much it. Of course, I could, if I want, say let r of x, y equal, let this be x, let this be y, and this will be the square root, oh, no square root. This will be 9 minus x squared, and I could take r sub x, r sub y, and cross the 2 and proceed. That will work out the same way. Even though I said I wasn't going to show this, I'm kind of tempted. So that is 1, 0, negative 2x. R sub y is 0, 1, 0. And if I take the cross product of those, r sub x cross with r sub y, that is, the I component will be 0 minus 2x, that's 2x. The j component will be 0, and the k component will be 1. And if I take the magnitude of that vector, that is the square root of 4x squared plus 1. There it is. And you could always play it that way. So again, no point in you converting from one to the other. It depends really what you like. Certain things you might want u and v, kind of like r and theta. And if it's a sphere, you really want spherical coordinates. How about this problem? I'm looking at a plane. A plane is really simple. So if both of those equal 0, x equals 6, y equal 4, 3, we're talking about the first octant only. There it is. There's the shadow. So how does that work? The double integral over s of x, xy plus z ds over s is going to equal what? Well, isn't that z equal 3 minus 3y over 4 minus 2x over 4? There it is. I could say, let's take the square root of f sub x, f sub y plus 1. That's the square root of 1/4 plus 9/16 plus 1 That is the square root of all over 16. 4 plus 9 plus 16. What is that? 16, 20, 29. So this is going to be the double interval. X, Y are fine. Z is 3 minus 3y over 4 minus x over 2 times the square root of 29 over 4. And I'm going to run dy, dx, dy. And if I look at this, the two dimensions look like this. X runs to 6, y runs to 4. We're talking about this region. If I zero this out, I'm looking at x running from 0 to 6, and y runs from 0 to, if this is 0, to 12 divided by 3, 4 minus 2x over 3. That'll do the trick. And the last example I have, of course, portion of a sphere and a cone. How does that work? Well, by now, I'm hoping you are as comfortable with this as I am. I'm looking at one of them. There we go. Well, how does that work? Well, to describe a sphere, I'm going to say r of theta and phi, despite the fact that I don't like that. Rho is 4. So 4, the cosine of theta, sine of phi. 4, the sine of theta, sine of phi. And 4, the cosine of phi. Again, it's a big mess, but it's easier than the alternative. If I take r sub theta, I've been putting an arrow on my, yeah, I have, okay, good. R sub theta, negative 4, the sine of theta, sine of phi, 4, the cosine of theta, sine of phi, and a 0. R sub phi is going to be 4, the cosine of theta, cosine of phi, 4, the sine of theta, cosine of phi, and negative 4, the sine of phi. Again, not pleasant, I know. R sub theta crossed with R sub phi is going to be the I component, those minus 0, negative 16, the cosine of theta, sine squared of phi, negative the j component, that's going to be 16, the sine of theta, sine squared of phi, minus 0. Very good. And the j component is the messy one. J component is going to be negative 16, the sine squared of theta, sine of phi, cosine of phi, minus the product of those. 16, the cosine squared of theta, sine of phi, cosine of phi. Of course, that's not, even though it looks really messy, that's not the tough part. The tough part is the magnitude of r of theta crossed with r sub phi is going to equal the square root of this squared, 16 squared, the cosine squared of theta, sine to the 4th of phi, plus this squared, 16 squared, the sine squared of theta, sine to the 4th of phi, and this squared. Does that clean up a bit before I go on and do something crazy? I could factor from the j component a negative 16, sine of phi, cosine of phi. I'll have sine squared of theta plus cosine squared of theta. Good. That's a 1. So that's what the last component is. Plus 16 squared, the sine squared of phi, cosine squared of phi. Now, if I look at this, that's the square root, and that's not ds because I'm still missing dA. They all have 16 squared. I could factor 16 out. I'll have, let me see, what's common in those? I notice they all have a sine squared of phi. I'll have a cosine squared of theta, sine squared of phi, plus sine squared of phi, sine squared of theta, and just a 1. So I'll get 16 the square root of the sine squared of phi. If I factor out of those two, a cosine, a sine squared of phi, I'll have cosine squared of theta plus sine squared of theta plus 1. That's a 1. So I'm looking at 16 the square root of sine to the 4th of phi. Oh, no. I could even factor that out. Sine of phi. And what I'll have left underneath the radical is simply the square root of sine squared of phi plus 1. Okay. I see a small mistake. I'll catch up with that. So again, a bit tedious. Take a 16 out. And let me look at those two. If I take the sine to the 4th of phi out, I'll have cosine squared of theta plus sine squared of theta plus sine squared of phi cosine squared of phi. So this is a 1. I'm left with the sine to the 4th of phi plus sine squared of phi cosine squared of theta. Of phi. So if I take the square root and factor a sine squared of phi, there it is. That's sine squared of phi plus cosine squared of phi. That's a 1. So this is 16 the square root of sine squared of phi. This is 16 the sine of phi. A lot of work, I understand. Students don't like it much, I understand. So the double integral over s of, what was the function? X plus z ds is going to equal the double integral, and let's see how this works. X is rho, the cosine of theta sine of phi, and rho we said was 16, or 4, plus z for the cosine of phi, times ds. ds is 16 the sine of phi. I'm going to take the integral. Phi is going to run from 0 to pi over 4, and theta is going to run from 0 to 2 pi, and that should do the trick, because, yeah, phi runs from 0 to pi over 4, we're used to that by now, and theta runs all around since it traces that thing. And that's pretty much it for this part. This is not the entire section, this is half of this. I needed to get comfortable with this before I move on to the next part of this section.